James Webb Space Telescope just found something that breaks cosmology. Not challenges, not questions, breaks. In July 2022, JWST turned its mirrors toward a patch of empty sky and captured the deepest image of the universe ever taken. And buried in that image, among thousands of distant galaxies, astronomers found something impossible. Galaxies that are 13.5 billion light-years away. That means we're seeing them as they were 13.5 billion years ago, when the universe was only 300 million years old. 300 million years. That's 2% of the universe's current age. The universe was an infant. And these galaxies? They're massive, containing 10 to 100 billion stars. They're bright, shining with the light of mature stellar populations. And some are structured, showing organization that shouldn't exist yet. Here's the problem. There wasn't enough time. Galaxy formation takes billions of years. You need multiple generations of stars forming, living, dying, enriching the gas with heavy elements, forming new stars. A slow, gradual process that we've observed, measured, and modeled for decades. But these galaxies somehow assembled in 300 million years. That's like finding a 2-year-old child who's 6 feet tall, has a master's degree, and runs a corporation. It doesn't make sense. It can't make sense. And yet, there they are, in the data, confirmed, real. So either our measurements are catastrophically wrong, which would mean JWST, the most advanced telescope ever built, is fundamentally broken, or our models are wrong, which would mean everything we think we understand about galaxy formation is incorrect, or cosmology itself is wrong, which would mean we need to rewrite 100 years of physics. None of these options are good. And astronomers? They're genuinely panicking. Papers are being published with titles like A Crisis in Cosmology and Panic at the Discotheque. Yes, that's a real paper title. Scientists don't usually panic in print, but this has them worried. By the end of this video, you'll understand exactly what James Webb discovered, why it shouldn't exist, and what it means for our understanding of the universe. Because this isn't just an interesting anomaly. This is a paradigm crisis, and we are watching it unfold in real time. Let's begin. Let me show you what JWST actually observed, because the images themselves don't look dramatic. They look like red smudges, tiny, faint reddish blobs scattered across deep field images. Easy to miss if you don't know what you're looking at. But when astronomers measured the redshift of these galaxies, the amount their light has been stretched by the expansion of the universe, they found something shocking. Redshifts of Z equals 10, 11, 12, even 13. Let me translate that. A redshift of Z equals 10 means you're looking back approximately 13.4 billion years. The universe was 400 million years old. A redshift of Z equals 13 means you're looking back approximately 13.5 billion years. The universe was only 300 million years old. For context, the oldest galaxies Hubble could see clearly were at Z equals 8 or 9, looking back about 13 billion years, when the universe was 600 to 700 million years old. JWST pushed that boundary, and what appeared at Z equals 10, 11, 12, 13 were galaxies that look mature, not tiny proto-galaxies still forming, not chaotic clumps of gas and a few stars. Full-fledged galaxies, with estimated masses of 10 billion, 50 billion, even 100 billion solar masses. That's 10 to 100 billion suns worth of stars, already assembled, shining, organized. And here's where it gets worse. Some of these galaxies are red. In astronomy, Red galaxies mean old galaxies, galaxies where star formation has slowed or stopped, where the massive blue stars have already died, leaving behind older, redder stars. Think about that. These galaxies formed stars, evolved, aged, and stopped forming new stars, all within 300 million years of the Big Bang. It's like finding teenagers who look and act like senior citizens. Their entire life cycle happened in a cosmic blink. One astronomer described them as universe breakers. Another said they're cosmological nightmares. These galaxies are cosmic teenagers with the bodies and life histories of adults. And according to everything we know about galaxy formation, they shouldn't exist. But they do. The data is clear. The images are real. The measurements have been checked and rechecked. Which means something is very, very wrong with our understanding of the early universe. We're going to understand this crisis from the ground up, step by step, so that by the end, you'll know exactly why astronomers are losing sleep over these galaxies. First, we'll explore the James Webb Space Telescope itself, how it works, why it can see farther back in time than Hubble, what makes it so powerful. Because understanding JWST's capabilities is crucial to understanding why these discoveries are reliable, not just errors or artifacts. Second, we'll dive into the early universe. What was it like 300 million years after the Big Bang? What physical conditions existed? How were galaxies supposed to form? This is the foundation, the accepted model that these observations are challenging. Third, we'll examine galaxy formation theory in detail, the step-by-step process by which gas collapses, stars form, galaxies grow, the timescales involved, the physical limits, why billions of years are required. This is what makes the JWST observations so shocking. Fourth, we'll look at the impossible galaxies themselves, one by one, their masses, their brightness, their ages, the data that's causing the crisis. Because this isn't one anomaly, it's dozens, a pattern that can't be ignored. Fifth, we'll explore the explanations. Are the measurements wrong? Is star formation faster than we thought? Do we need new physics? Are our cosmological models fundamentally flawed? We'll weigh each possibility, examine the evidence, and confront the uncomfortable truth that none of the easy answers work. Finally, we'll discuss what this means for astronomy, for cosmology, for our understanding of cosmic history. Whether this is a crisis that redefines astrophysics or a puzzle that refines our models without breaking them. This isn't just a story about distant galaxies. This is a story about the scientific process confronting the unexpected, about what happens when observations don't match theory, about the possibility, remote but real, that we're witnessing a paradigm shift. 100 years ago, Edwin Hubble discovered the universe was expanding. That single observation forced a complete rethinking of cosmology and led to the Big Bang theory. Could these JWST observations be another watershed moment? We don't know yet, but the fact that serious scientists are asking the question tells you how significant this is. These galaxies are cosmic impossibilities. You're going to understand exactly why. Let's start with the telescope that found them. We've established the paradox. Massive mature galaxies at Z equals 10, 11, 12, 13, existing when the universe was only 300 million years old, defying our models of galaxy formation. But before we can appreciate why this is impossible, we need to understand the instrument that made these discoveries. Because James Webb isn't just a better Hubble, it's a fundamentally different kind of telescope, designed specifically to peer into the early universe, to see what Hubble couldn't. And understanding JWST's capabilities is crucial to understanding why these observations are trustworthy, why they're not just measurement errors or instrumental artifacts. JWST was built to find early galaxies. It succeeded beyond anyone's expectations, and what it found has astronomers questioning everything. Let's see how it works. The Hubble Space Telescope revolutionized astronomy. For over 30 years, it gave us unprecedented views of the cosmos. Deep fields revealing thousands of galaxies, measurements of the universe's expansion, images that became icons. But Hubble has limits. Hubble primarily observes invisible and ultraviolet light, the wavelengths our eyes can see, plus slightly shorter wavelengths. Its mirror is 2.4 meters in diameter. Impressive, but not large enough to gather light from the very faintest, most distant objects. And here's Hubble's fundamental limitation for studying the early universe. The farther away a galaxy is, the more its light has been redshifted by the expansion of the universe. Light from distant galaxies stretches as space itself expands, like a wave on a stretching rubber sheet. The wavelength gets longer. Blue light becomes red. Red light becomes infrared. Infrared becomes far infrared. Galaxies at redshift Z equals 8 or 9, the most distant Hubble could see clearly, have their ultraviolet light redshifted into visible wavelengths. Their visible light redshifts into near-infrared. Hubble can detect some near-infrared, but it's not optimized for it. Galaxies at Z equals 10, 11, 12, 13. Their light is redshifted so much that it's almost entirely in the infrared. Wavelengths Hubble struggles to detect. For Hubble, these galaxies are invisible or extremely faint, like trying to see in the dark with sunglasses on. Enter James Webb. JWST was designed specifically to observe in infrared wavelengths, from near-infrared to mid-infrared, wavelengths between 0.6 and 28 microns. Its primary mirror is 6.5 meters in diameter, nearly 3 times larger than Hubble's. More surface area means more light gathering power. In terms of sensitivity, JWST is approximately 100 times more powerful than Hubble for infrared observations. That's not an incremental improvement. That's a revolution. And here's why it matters. The infrared universe is invisible to human eyes, but crucial for studying the early universe. Because every distant galaxy's light gets redshifted into infrared. JWST doesn't just see farther than Hubble, it sees in wavelengths where the early universe actually shines. But there's a catch. Infrared light is heat. Everything warm emits infrared radiation, including the telescope itself. So, JWST operates at cryogenic temperatures, around 40 Kelvin, or minus 233 degrees Celsius. That's colder than Pluto. The telescope is actively cooled to prevent its own heat from overwhelming the faint signals from distant galaxies. It sits at the L2 Lagrange point, 1.5 million kilometers from Earth, on the opposite side from the Sun. A gravitationally stable location where Earth and Sun are always in the same direction, allowing a single sun shield to block their heat. That sun shield is the size of a tennis court, 5 layers of material, each thinner than a human hair. It keeps the telescope in perpetual shadow, maintaining those cryogenic temperatures. JWST doesn't orbit Earth, it orbits empty space, 1.5 million kilometers away, slowly circling the L2 point, constantly staring into the cosmic dark. It launched on December 25th, 2021, spent 6 months unfolding, calibrating, cooling down, and became fully operational in July 2022. Within weeks of starting science observations, it was already finding galaxies Hubble never saw, and within months, it was finding galaxies that shouldn't exist. Let's talk about what it means to see back in time. Because this isn't science fiction, this is just physics. Light travels at 299,792 kilometers per second. That's fast, incomprehensibly fast by human standards. But it's finite. Light doesn't travel instantaneously across the universe. When you look at the sun, you're seeing it as it was 8 minutes and 20 seconds ago. That's how long sunlight takes to travel 150 million kilometers to Earth. When you look at Proxima Centauri, the nearest star, you're seeing it as it was 4.24 years ago. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago. The light left Andromeda when early hominids were just learning to use stone tools. Distance equals time. The farther away something is, the farther back in time you're seeing it. Now scale that up. A galaxy 1 billion light years away? You're seeing it as it was 1 billion years ago. When the universe was 12.8 billion years old? A galaxy 10 billion light years away? You're seeing it as it was 10 billion years ago, when the universe was only 3.8 billion years old. A galaxy 13 billion light years away? You're seeing it as it was 13 billion years ago, when the universe was less than a billion years old. JWST has detected galaxies at look-back times of 13.4 to 13.5 billion years. That means the light we're seeing left those galaxies when the universe was only 300 to 400 million years old. To put that in perspective, if the universe's current age, 13.8 billion years, were compressed into a single year, we'd be seeing these galaxies as they were on January 7th, 1 week into the cosmic calendar. Or think of it this way. If the universe were a 50-year-old person, we're seeing photographs from when it was 13 days old, less than 2 weeks, an infant. These are the earliest, most distant objects ever observed by humanity. We're looking at cosmic nurseries, the universe's childhood, the epoch when the first galaxies were just beginning to form. Except these babies look like giants. The redshift, that stretching of light, gives us a direct measurement of distance and age. Higher redshift equals farther away equals earlier in cosmic history. Redshift Z equals 1. Universe was about 6 billion years old. Redshift Z equals 2. Universe was about 3 billion years old. Redshift Z equals 6. Universe was about 1 billion years old. Redshift Z equals 10. Universe was about 400 million years old. Redshift Z equals 13. Universe was about 300 million years old. JWST has found galaxies at Z equals 10, 11, 12, and possibly 13 or higher. We are literally observing the universe in its infancy, peering back across 97% of cosmic history, seeing galaxies that formed when the universe was 2% of its current age. And here's what makes it profound. These galaxies have been gone for over 13 billion years. We're not seeing them as they are. We're seeing them as they were. The light has been traveling through expanding space for 13.5 billion years, finally reaching Earth in 2022, entering JWST's mirrors, triggering detectors, becoming data. Those galaxies today, in the present moment, 13.8 billion years after the Big Bang, are unimaginably different. They've merged with other galaxies, formed trillions of new stars, maybe became massive ellipticals, or maybe they were torn apart in collisions and no longer exist as coherent structures. We'll never know. We can only see their past, the light that left when the universe was young. But that past, that 300 million year old universe, is where the mystery lies. Because according to everything we know about physics, those galaxies shouldn't have been there. On July 12th, 2022, NASA released JWST's first deep field image. They called it SMACS 0723, a galaxy cluster about 4.6 billion light-years away. But the cluster itself wasn't the target. The cluster was a gravitational lens, its mass bending space-time, magnifying light from galaxies behind it. The image showed thousands of galaxies, some nearby, some distant, some impossibly far. And it was the deepest, sharpest infrared image of the universe ever captured. Astronomers immediately began analyzing it, measuring redshifts, calculating distances, estimating masses, and they started finding surprises. Galaxies at Z equals 10. Not just one or two. Several. Far more than expected based on Hubble's surveys. Galaxies that were brighter than predictions suggested they should be. Galaxies with estimated stellar masses that seemed too high for their age. The scientific community was excited. We're seeing the early universe in unprecedented detail. Papers started getting written. Data started getting analyzed. And then, in August 2022, a team announced something stunning. They'd found a galaxy candidate at redshift Z equals 13.1. They called it Glass Z13. If confirmed, this galaxy existed just 300 million years after the Big Bang, one of the most distant galaxies ever detected. But it wasn't just distant. It was massive. Initial estimates suggested a stellar mass around 1 billion solar masses. 1 billion stars. Already formed. Already shining. At Z equals 13. The team was cautious. They noted it needed spectroscopic confirmation, direct measurement of the redshift through spectra, not just photometry, measuring brightness in different filters. But the photometric redshift was solid. The galaxy was real, and it was far more massive than models predicted should exist at that epoch. Then came more candidates. Sears 9, 3, 3, 1, 6, initially reported at Z equals 16.7, later revised downward, but still significant. Multiple Z equals 10 to 12 candidates from the Sears, Cosmic Evolution, Early Release Science Survey. Several Z equals 11 plus galaxies from the JADES, JWST Advanced Deep Extragalactic Survey Program. Within 6 months of JWST starting science operations, astronomers had catalogued dozens of candidate galaxies at Z greater than 10, and many of them shared disturbing characteristics. Too bright. Luminosities suggesting mature stellar populations, not just the first generation of stars. Too massive. Stellar masses estimated at 10 billion, 50 billion, even 100 billion solar masses. Too red. Colors indicating old stellar populations, red giants and red supergiants, not the hot blue stars you'd expect in young galaxies. Too numerous. The sheer number of high redshift galaxies was greater than models predicted, and some showed hints of structure. Not perfect spirals, nothing that organized, but hints of disks, suggestions of central bulges, clumpiness that looked more organized than the chaotic proto-galaxies models predicted. By early 2023, the papers started rolling in with increasingly alarmed titles. A crisis in cosmology? Panic at the discotheque. Are JWST high redshift galaxies consistent with lambda CDM? Accelerated galaxy growth and quenching at high redshift. A population of red candidate massive galaxies at 600 million years after the Big Bang. That last one is particularly troubling. Red candidate massive galaxies at Z equals 10 plus. Galaxies that have already aged. Astronomers started using phrases like tension with theory and challenge to models, and, increasingly, inconsistent with standard galaxy formation. The data wasn't going away. spectroscopic confirmation started coming in for many candidates, proving they really were at Z equals 10 plus. And the problem became clear. These galaxies exist. They're real. They're massive. And they shouldn't be. Because to understand why, we need to understand what the early universe was actually like, and how galaxies are supposed to form. That's where we're going next. We've established that JWST can see farther back in time than Hubble, that it found dozens of massive bright galaxies at Z equals 10 to 13, that these observations have been confirmed and are reliable. Now we need to understand the universe they existed in. What was the cosmos like 300 million years after the Big Bang? What physical conditions existed? What processes were happening? And most importantly, how are galaxies supposed to form? Because until you understand the accepted model, the framework built over decades of observations and confirmed by Hubble, you can't appreciate why these JWST discoveries are so shocking. The universe 300 million years after the Big Bang was nothing like today. It was hotter, denser, simpler, still cooling from the Big Bang's primordial heat. No galaxies existed yet, at least not according to our models. Just gas, dark matter, and time. Let's go back to the beginning. Let's rewind to the beginning, to the Big Bang, 13.8 billion years ago. In the first fractions of a second, the universe was unimaginably hot and dense, temperatures exceeding trillions of degrees, energy so concentrated that matter and antimatter continuously formed and annihilated, quarks and gluons existing as free particles in a plasma so hot that atoms couldn't exist. Then cosmic inflation happened, that exponential expansion we discussed in the previous video. The universe grew by a factor of at least 10 to the 26th power in a fraction of a second. After inflation ended, the universe continued expanding, but more slowly. It was still incredibly hot, billions of degrees, but cooling as it expanded. For the first 380,000 years, the universe was opaque, a fog of plasma. Electrons and protons existed as separate particles, constantly interacting with photons. Light couldn't travel freely. It would scatter off electrons after traveling tiny distances. If you could somehow exist back then, you wouldn't see anything. Not because it was dark. It was incredibly bright, glowing with thermal radiation. But because light couldn't travel. Everything was a glowing fog. Then, at 380,000 years, something crucial happened. Recombination. The universe had cooled enough to about 3,000 Kelvin for electrons to combine with protons, forming neutral hydrogen atoms. Suddenly, photons could travel freely. Light was no longer constantly scattered by free electrons. The universe became transparent. This moment is frozen in the cosmic microwave background, the CMB. That ancient light, now redshifted from visible wavelengths to microwaves, fills the entire sky. It's a photograph of the universe at 380,000 years old. And here's what the CMB tells us. The universe was remarkably smooth. Temperature variations of only a few parts per 100,000. Density variations at the same level. Nearly uniform, nearly homogeneous, but not perfectly uniform. There were tiny fluctuations, quantum fluctuations from inflation, stretched to cosmic scales. Regions that were slightly denser than average. Regions that were slightly less dense. And those tiny variations, millionths of a degree in temperature, were the seeds of all structure in the universe. After recombination, the universe entered what astronomers call the Dark Ages. No stars existed yet, just neutral hydrogen gas, filling space. The universe was dark, completely dark. The only light was the fading afterglow of recombination, the CMB, redshifting into longer and longer wavelengths. The temperature dropped from 3000 Kelvin to hundreds of Kelvin to tens of Kelvin. The universe cooled as it expanded, and in those denser regions, the ones seeded by quantum fluctuations, gravity began to work. Slowly, imperceptibly at first, but inevitably, denser regions attracted more matter. Dark matter, which makes up 85% of the universe's matter but doesn't interact with light, began collapsing into halos, gravitationally bound structures. Normal matter, hydrogen and helium gas, fell into these dark matter halos. Gas clouds compressed, heated, collided. And somewhere around 100 to 200 million years after the Big Bang, in the densest halos, the first stars ignited. These weren't like stars today. They were massive, 100 to 300 times the mass of the Sun, incredibly hot, blazing with ultraviolet light, burning through their fuel in just a few million years. They're called Population 3 stars, the first generation, made entirely of hydrogen and helium. No heavy elements, because heavy elements hadn't been created yet. They lived fast and died young. Supernovae after a few million years, seeding the surrounding gas with the first heavy elements: carbon, oxygen, nitrogen, silicon, iron. This was the reionization epoch. The ultraviolet light from these first stars began ionizing the neutral hydrogen gas, turning the universe transparent to UV light. The Dark Ages ended. This process took time, hundreds of millions of years. The universe gradually lit up as more and more stars formed. More and more gas was ionized. By 500 million years after the Big Bang, reionization was well underway. By 1 billion years, it was mostly complete. But at 300 million years, where JWST is finding these massive galaxies, reionization had barely begun. The universe was still mostly neutral. Most regions were still dark. The first stars had just started forming in the densest halos. And according to our models, galaxies, real, massive galaxies containing billions of stars, shouldn't exist yet. Because galaxy formation is slow. Let's understand the process by which galaxies form, step by step, because the timescales matter. It starts with those tiny density fluctuations from inflation, regions where matter is slightly denser than average. Step 1. Dark matter halos form. Dark matter doesn't interact with normal matter except through gravity. That's actually an advantage for structure formation, because dark matter isn't affected by radiation pressure or gas pressure. It just collapses under its own gravity. In overdense regions, dark matter begins clumping. Small halos form first, maybe 1 million solar masses. These halos merge, forming larger halos. The process is hierarchical. Small structures merge to form bigger structures. By 100 million years, dark matter halos with masses of 10 to the power of 6 to 10 to the power of 8 solar masses have formed. These are the scaffolding for the first galaxies. Timeline: 50 to 100 million years. Step 2. Gas falls into dark matter halos. Normal matter, hydrogen and helium gas, is pulled into these dark matter halos by gravity. But gas can't collapse as efficiently as dark matter, because gas has pressure. When gas falls into a halo, it compresses. Compression heats it. Hot gas has pressure that resists further collapse. The gas needs to cool to continue collapsing. Cooling happens through radiation. Atoms collide, get excited, emit photons, lose energy. In the early universe, with only hydrogen and helium, cooling is slow. Hydrogen atoms don't radiate efficiently. It takes time for gas to cool enough to collapse further. Timeline: 10 to 50 million years for gas to settle into halos. Step 3. First stars form. Once gas cools and becomes dense enough, typically in the centers of dark matter halos, it fragments into clumps that collapse further. When a clump reaches sufficient density and temperature, nuclear fusion ignites. A star is born. The first stars were massive, 100 plus solar masses, because the gas was purely primordial. No heavy elements to help it cool and fragment into smaller clumps. These massive stars burned bright and hot. They ionized surrounding gas. They produced stellar winds, and they died young, 3 to 10 million years, exploding as supernovae. Timeline: 100 to 200 million years for the first stars to form and die. Step 4. Gas enrichment and second-generation stars. Supernova explosions disperse heavy elements, carbon, oxygen, iron, into the surrounding gas. This enriched gas can cool more efficiently than pure hydrogen. Second-generation stars form from this enriched gas. They can be smaller, more like modern stars. Their lifetimes are longer, but this process takes time. Gas needs to cool again after being heated by supernovae. New stars form. More supernovae enrich more gas. The cycle repeats. Timeline: 50 to 100 million years per generation. Step 5. Halo mergers and galaxy assembly. While stars are forming, dark matter halos continue merging. Small halos combine into larger halos. Each merger brings new gas. New bursts of star formation. The process is chaotic. Halos collide. Gas shocks. Stars form in bursts. Supernovae disrupt gas clouds, temporarily halting star formation. Over hundreds of millions of years, this chaotic process gradually assembles a galaxy, a gravitationally bound system of stars, gas, and dark matter. But hundreds of millions of years is the key phrase. Timeline: 300 to 500 million years for a significant galaxy to assemble. Add all of this up, and here's the picture. 100 million years, first dark matter halos. 200 million years, first stars. 300 million years, multiple stellar generations, modest star formation. 400 to 500 million years, first real galaxies with billions of stars. 1 billion years, mature galaxies starting to look organized. This is the standard model of galaxy formation, built over decades, tested against Hubble observations, confirmed by computer simulations, and it says, at 300 million years after the Big Bang, you should have proto-galaxies, small, irregular clumps containing maybe 1 billion stars maximum. Chaotic, actively forming stars. No structure, not massive galaxies with 100 billion stars. Not galaxies that have already aged and turned red. Not organized structures. Those should take 1 billion years minimum to form. But JWST is finding them at 300 million years. Let's make this concrete with specific numbers, because when astronomers say these galaxies shouldn't exist, they mean the math doesn't work. Here's the normal galaxy formation timeline, based on decades of observations. 300 million years after Big Bang, Z approximately 15 to 20. First stars just forming. Tiny proto-galaxies, 10 to the power of 6 to 10 to the power of 8 solar masses, 1 million to 100 million stars. Highly irregular, chaotic, extremely faint. Star formation rate, approximately 0.1 to 1 solar mass per year. Expected to be rare, very few per cosmic volume, 500 million years at Z approximately 10. Proto-galaxies growing. Masses, 10 to the power of 8 to 10 to the power of 9 solar masses, 100 million to 1 billion stars. Still irregular, but more substantial. Active star formation rate, approximately 1 to 10 solar masses per year. Still relatively uncommon, 1 billion years, Z6. Real galaxies emerging, masses, 10 to the power of 9 to 10 to the power of 10 solar masses, 1 billion to 10 billion stars. Some beginning to show structure, hints of disks. Vigorous star formation rate, approximately 10 to 100 solar masses per year. More common, but still developing, 2 billion years, Z, 3 to 4. Mature galaxies, masses, 10 to the power of 10 to 10 to the power of 11. Solar masses, 10 billion to 100 billion stars. Clear structure, disks, bulges, spiral arms beginning. Sustained star formation rate, approximately 10 to 100 plus solar masses per year. Common across cosmic volumes, 5 to 7 billion years, seed 1 to 2. Peak of galaxy formation. Massive galaxies, 10 to the 11th plus solar masses, 100 billion plus stars. Beautiful spiral and elliptical structures. Peak star formation rate in cosmic history. Galaxies everywhere. Now here's the key constraint. Star formation rate. Even in the most extreme starburst galaxies we observe today, galaxies undergoing rapid bursts of star formation triggered by mergers, the maximum sustained star formation rate is about 1,000 solar masses per year. That's extreme. Most galaxies form stars at 1 to 10 solar masses per year. The Milky Way currently forms about 1 to 2 solar masses per year. But let's be generous. Let's assume early galaxies could sustain 100 solar masses per year. That's already 50 to 100 times higher than normal galaxies. In 300 million years, at 100 solar masses per year, you could form 100 solar masses per year times 300 million years equals 30 billion solar masses. Okay, that's actually pretty substantial. Maybe enough to explain a 30 billion solar mass galaxy. But here's the problem. That assumes 100% efficiency, that every bit of gas becomes stars, that nothing is lost to stellar winds, supernova, outflows. In reality, star formation efficiency is about 1 to 10%. Most gas does not become stars. It's heated by supernovae and blown out of the galaxy, or it remains as cold gas that hasn't collapsed yet. With 10% efficiency, that 30 billion solar masses becomes 3 billion. With 1% efficiency, it's 300 million solar masses. That's what models predict for 300 million years. Proto-galaxies with hundreds of millions to a few billion solar masses. Not 50 billion, not 100 billion. And certainly not galaxies that have already stopped forming stars. Because that would require forming all those stars early, letting them age and exhausting the gas supply, all in less than 300 million years. The math simply doesn't work. When JWST was being designed and built, astronomers made predictions about what it would find in the early universe. These predictions were based on the Standard Model, decades of theory and Hubble observations, computer simulations, modeling galaxy formation, extrapolations from known physics. Here's what astronomers expected JWST to see at Z equals 10 to 13. Expected small, faint proto-galaxies. Masses 10 to the power of 8 to 10 to the power of 9 solar masses, 100 million to 1 billion stars. Brightness faint. Among the faintest objects JWST could detect. Structure highly irregular, clumpy, chaotic. Colors blue, indicating hot, young, massive stars. Star formation active, ongoing, vigorous. Numbers relatively rare. Finding a few dozen would be exciting. Expected population 3 star signatures. The first generation of stars made purely of hydrogen and helium. Different spectral signatures from later stars, possibly visible as individual sources or small clusters. Evidence of pristine gas with no heavy elements. Expected reionization in action. The process of ultraviolet light ionizing neutral hydrogen. Galaxies surrounded by bubbles of ionized gas. The universe transitioning from neutral to ionized. Expected simple morphologies. No spiral arms, those require billions of years. No central bulges, those form from mergers over time. No clear disks, rotation and settling take time. Just irregular clumps and blobs. There was excitement. JWST would let us see galaxy formation happening. We'd watch the universe light up. We'd see the first stars. We'd witness cosmic dawn. Papers were written with predictions. Simulations were run. Instruments were calibrated. Observing programs were designed. The science team was confident. The models were solid. We knew what early galaxies should look like. And then JWST turned on. And within weeks, astronomers were saying, wait, these galaxies are too bright. Within months, these masses are too high. Within a year, these galaxies shouldn't exist. What JWST actually found at Z equals 10 to 13. Reality. Large, bright galaxies. Masses. 10 to the power of 9 to 10 to the power of 11. Solar masses. 1 billion to 100 billion stars. Brightness. Much brighter than predicted, easily detected, not pushing detection limits. Structure. Some show hints of organization, possible disks, central concentrations. Colors. Many are red, indicating old stellar populations. Star formation. Some are still active, but some appear quiescent. Star formation stopped. Numbers. Far more abundant than predicted. The discrepancy is huge, not a minor refinement to models, not a factor of 2 or 3. Some of these galaxies are 10 to 100 times more massive than predictions. They're 10 times more numerous than expected. And some have properties, red colors, massive sizes, possible structure, that shouldn't exist for another billion years. This isn't a small problem. This is models predicting X and observations showing 10x or 100x. In a 2023 paper, astronomers wrote, "The number density of massive galaxies at Z greater than 10 exceeds predictions by at least an order of magnitude." An order of magnitude. That's a factor of 10. Predictions were off by a factor of 10. Another paper. If confirmed, these galaxies are inconsistent with standard models of galaxy formation. Inconsistent with standard models. That's scientific language for, we don't know how this is possible. The models weren't slightly wrong. They were dramatically wrong. And that means either the observations are wrong, which seems increasingly unlikely as spectroscopic confirmations roll in, or the models are wrong. And if the models are wrong, we need to figure out why. What are we missing? What physics did we not account for? What assumption is incorrect? Because this isn't just about a few weird galaxies. This is about understanding how the universe evolved from the Big Bang to today. If galaxy formation happened much faster than we thought, that has implications for everything. Dark matter properties, star formation physics, the nature of early universe conditions. This is a paradigm challenge, and it demands an explanation. We've established the problem. We've shown you what galaxies should look like at 300 million years after the Big Bang. Small, faint, irregular, actively forming their first generations of stars. We've shown you what JWST actually found. Massive, bright, possibly structured galaxies, some already old and red, existing when they shouldn't. Now we need to see these galaxies up close, one by one, the data, the measurements, the specific objects that are causing astronomers to lose sleep, because this isn't abstract theory. These are real galaxies, with measured redshifts, estimated masses, observed properties, and every single one is a cosmic impossibility. Let's meet them. Let's start with one of the most famous and controversial early discoveries, Glass Z13. Discovered in August 2022 by a team analyzing JWST data from the GLASS Grism Lens Amplified Survey from Space program, published in a preprint that sent shockwaves through the astronomical community. The measurements: photometric redshift, Z equals 13.1 plus or minus 0.1. That places it approximately 13.5 billion light-years away in comoving distance. The light we see left this galaxy when the universe was only 300 million years old. Apparent magnitude, relatively bright for such a distant object. Not at JWST's detection limit, easily detected. Estimated stellar mass: approximately 1 billion solar masses, 1 billion stars worth of mass, already assembled, already shining, at 300 million years after the Big Bang. Let's do the math on whether this is possible. If we assume star formation began at 100 million years, optimistic, that's when the first stars formed. That gives 200 million years of star formation, time, at an extreme star formation rate of 100 solar masses per year, already 50 times higher than the Milky Way's current rate. You could form 20 billion solar masses, but with realistic efficiency of 5 to 10%, that becomes 1 to 2 billion solar masses. So, barely possible? If everything went perfectly? If star formation started immediately, proceeded at maximum rates with no interruptions, and efficiency was at the high end? Maybe. Just maybe. But here's the issue. Glass Z13 isn't unique. It's not an isolated outlier that could be explained as a statistical fluke. There are dozens of similar galaxies, and some are even more extreme. The team was cautious in their paper. They noted this needed spectroscopic confirmation. Photometric redshifts can be wrong. You're estimating distance from colors, not from direct spectral measurements. And they were right to be cautious, because soon after, other discoveries made Glass Z13 look almost normal. Glass Z12, found in the same survey. Redshift Z equals 12.4. Age: approximately 350 million years. Estimated mass: 1 to 2 billion solar masses. Similar properties, similar impossibility. Then the SEERS, Cosmic Evolution, Early Release Science, survey started releasing results. Maisie's galaxy, named after the discoverer's daughter. Redshift, Z equals 11.4, spectroscopically confirmed. Age: approximately 400 million years after Big Bang estimated mass. Approximately 100 million to 1 billion solar masses. This one got spectroscopic confirmation using JWST's NIR spec instrument. The redshift is solid, not photometric. Direct measurement from spectral lines. The galaxy exists. It's really that far away, and it's really that massive. And then came the real shockers. The galaxies that didn't just challenge models, they seemed to obliterate them. Let me introduce you to the truly extreme cases. The galaxies that make astronomers question everything. In February 2023, a paper was published in Nature with a remarkable claim. They'd found 6 massive galaxy candidates at redshifts Z equals 7.4 to 9.1. That's 600 to 700 million years after the Big Bang. Slightly later than Glass Z13, but still incredibly early. The paper's title was cautious: A population of red candidate massive galaxies approximately 600 million years after the Big Bang. But the content was explosive. Estimated masses: 10 to 100 billion solar masses. Let me repeat that. 100 billion solar masses. That's comparable to the Milky Way's current stellar mass, assembled in less than 700 million years. The most extreme candidate, estimated at 100 billion solar masses at Z equals 7.4. That's 13.1 billion years ago. Universe age, 700 million years. If star formation started at 200 million years, realistic, that's 500 million years to assemble 100 billion solar masses. At 100 solar masses per year, again, an extreme rate, you could form 50 billion solar masses. With 10% efficiency, that's 5 billion solar masses. This galaxy is 20 times more massive than that. You'd need star formation rates of 2,000 solar masses per year, sustained, for 500 million years. With 10% efficiency, 2,000 solar masses per year. That's double the maximum rate ever observed in the most extreme starburst galaxies in the modern universe, sustained for 500 million years. The authors wrote, "If even one of these galaxies is confirmed, our understanding of galaxy formation is significantly challenged. Not refined, not updated, challenged." But it wasn't just these 6. The discoveries kept coming. JWST 13-0, discovered in the JADES, JWST, Advanced Deep Extragalactic Survey program. Redshift, Z equals 13.2, spectroscopically confirmed. Age, approximately 325 million years. Properties, compact, bright, with evidence of ongoing star formation. Estimated mass, approximately 500 million to 1 billion solar masses. Spectroscopic confirmation. The distance is certain. The galaxy is real. JWST 14. 0. This one set a record when announced in 2024. Redshift. Z equals 14.32. Spectroscopically confirmed with NIR spec. Age, approximately 280 million years after Big Bang. This is one of the most distant spectroscopically confirmed galaxies ever found. Light from this galaxy has been traveling for 13.5 billion years. Estimated mass, approximately 500 million solar masses. Size, surprisingly large, about 1,600 light-years across. For comparison, at this age, models predict proto-galaxies maybe a few hundred light-years across. But here's what makes these discoveries particularly troubling. It's not just one galaxy. It's not an outlier. Across multiple surveys, GLASS, SEERS, JADES, UNCOVER, and others, astronomers have found dozens of massive galaxy candidates at Z greater than 10. A 2023 census counted over 30 candidate galaxies at Z greater than 10, with stellar masses exceeding 1 billion solar masses. And more are being discovered monthly as new JWST data gets analyzed. The number density, how many massive galaxies exist per unit volume of space, is approximately 10 times higher than models predicted. That's not a small discrepancy. That's a factor of 10 mismatch between theory and observation. Let's focus on the central problem. Stellar mass. Building stars takes time. You need gas to collapse, stars to form, stars to live, stars to die, gas to be enriched, new stars to form from enriched gas. Each generation takes millions of years minimum. More realistically, tens of millions of years. And you can only form stars as fast as gas can cool and collapse. That rate is limited by physics. Gas collapses when gravity overcomes pressure. Gas cools by radiating energy. The cooling rate depends on density, temperature, and composition. In the early universe, with only hydrogen and helium, cooling is slow. Hydrogen doesn't radiate efficiently. It takes time. Even with perfect conditions, maximum density, ideal temperatures, there's a physical limit to how fast gas can collapse and form stars. Simulations suggest maximum sustained star formation rates in early galaxies of approximately 100 solar masses per year. That's already extreme. Most models predict 10 to 50 solar masses per year. Now let's calculate what these JWST galaxies would require. Example: a 50 billion solar mass galaxy at Z equals 10. Age: 400 million years. Assume star formation started at 150 million years. Optimistic. That gives 250 million years of star formation time to assemble 50 billion solar masses in 250 million years. But that's assuming 100% efficiency. Every bit of gas becomes stars. Impossible. Stellar winds and supernovae eject most gas. Realistic efficiency: 5 to 10%. With 10% efficiency, you need to process 2,000 solar masses per year of gas to form 200 solar masses of stars. With 5% efficiency, you need to process 4,000 solar masses per year, 4,000 solar masses per year, of gas inflow, cooling, collapse, and star formation, sustained for 250 million years. That's 40 times higher than maximum rates observed in the most extreme starburst galaxies today. And remember, these are galaxies in the early universe. Smaller dark matter halos, less total gas available, less efficient cooling. They should form stars slower than modern galaxies, not faster. But to exist, they had to form stars 40 times faster. The physics doesn't work unless something is different. Some mechanism we don't understand. Some process operating in the early universe that doesn't operate today. But what? Option 1. Top-heavy initial mass function, IMF. Maybe early stars were preferentially massive. More high-mass stars, fewer low-mass stars. High-mass stars shine brighter. They'd make galaxies appear more luminous for a given number of stars. Problem: this would make galaxies appear brighter without necessarily making them more massive. The stellar mass estimates would be lower, not higher. So this doesn't solve the problem. If anything, it makes it worse. Option 2. Extremely efficient star formation. Maybe early galaxies converted gas to stars with 50% or even 90% efficiency instead of 5 to 10%. Problem: supernovae and stellar winds are universal. Massive stars explode. They blow gas out of galaxies. This happens everywhere, always. You can't avoid it. It's fundamental to how star formation works. And if efficiency were that high, we'd see evidence in other observations: galaxy masses, gas content, metallicity. We don't. Option 3. Earlier start to star formation. Maybe star formation began at 50 million years instead of 100 to 150 million years. Problem: this requires the first stars to form much earlier than models predict. But we have constraints on this from other observations: the epoch of Ryanization, the CMB, observations of the earliest quasars. Starting earlier helps a little, but not enough to explain factors of 10 to 100 times excess mass. Option 4. Measurement errors. Maybe the stellar masses are overestimated. Maybe these galaxies are less massive than we think. Problem: multiple independent teams using different methods get similar results, and spectroscopic confirmations are now proving the redshifts are correct. The galaxies exist. They're really that distant. And mass estimates, while uncertain, are based on solid physics. None of the easy explanations work, which means either we're missing something fundamental about how star formation worked in the early universe, or the problem is even deeper. Now let me introduce you to the most disturbing class of galaxies JWST has found. The ones that aren't just massive. They're massive and red. In astronomy, color tells you about stellar populations. Blue galaxies are actively forming stars. Hot, massive, blue stars dominate their light. Red galaxies have stopped forming stars. The blue stars have died, leaving behind cooler, redder stars. Galaxy evolution typically works like this. Galaxies form stars vigorously for 1 billion or more years, shining blue. Eventually, they exhaust their gas or something shuts off star formation. They quench. Over hundreds of millions of years, the massive blue stars die, and the galaxy fades to red. This transition takes time. Massive stars live only a few million years, but they're bright. Once they're gone, the galaxy dims and reddens as lower mass stars, which are cooler and redder, dominate the light. The process of quenching, shutting off star formation, and then fading to red typically takes 500 million to 1 billion years. Minimum. But JWST is finding red galaxies at Z equals 10 to 12. Galaxies that have already gone through this entire cycle. Formation, vigorous star formation, quenching, fading to red, all within 300 to 500 million years after the Big Bang. A 2023 paper identified several quiescent, non-star-forming galaxy candidates at Z approximately 10 to 11. Properties: red colors indicating old stellar populations, little to no ongoing star formation, estimated ages of 100 to 300 million years for their stellar populations, masses of 10 to 40 billion solar masses. Think about the timeline this requires. Let's say the universe is 400 million years old. These galaxies form stars from, say, 150 million years to 300 million years. That's 150 million years of star formation. They then stopped forming stars, quenched, and they've aged for another 100 million years, long enough for the blue stars to die and the galaxy to turn red. This means 1. Massive star formation for 150 million years at extreme rates. 2. Complete shutdown of star formation. Something removed all the gas or heating prevented collapse. 3. Aging for 100 million years until blue stars died, all before the universe was 400 million years old. In the modern universe, this process takes 2 to 3 billion years minimum. These galaxies somehow compressed that timeline by a factor of 10. One paper described them as impossibly early quiescent galaxies. Another used the phrase cosmic fossils, galaxies that lived and died before most galaxies were even born. What could quench star formation that early? In modern galaxies, star formation is shut off by supermassive black holes at galactic centers, producing jets and winds that heat gas, galaxy mergers that disrupt gas disks, environmental effects in dense galaxy clusters, but at Z equals 10 to 11. Supermassive black holes shouldn't be massive enough yet to shut down entire galaxies. Galaxy mergers should trigger star formation, not suppress it. Dense clusters don't exist yet. Galaxies are isolated. So what shut off star formation in these galaxies? We don't know. And that's terrifying to astronomers, because if you don't know what stops star formation, you don't understand galaxy evolution. The existence of red, quiescent galaxies at Z equals 10 plus doesn't just challenge star formation models. It challenges our understanding of the entire life cycle of galaxies. One astronomer I spoke to, off the record, said, These red galaxies make me question everything. If galaxies can evolve this fast, maybe our entire framework is wrong. Maybe galaxies in the early universe obeyed completely different rules. Another wrote in a paper, the detection of even a single quiescent galaxy at these redshifts would require a radical revision of our models. They've found multiple candidates, not one, multiple. These galaxies lived entire lives, birth, growth, maturity, retirement, in the time it should have taken them just to be born. They're cosmic teenagers with grey hair and retirement plans. And they shouldn't exist. We've seen them now. The impossible galaxies. Glass Z13, Maisie's galaxy, JWST 14-0. The 6 massive candidates at Z equals 7 to 9. The red quiescent galaxies that have already aged. Dozens of galaxies. All at Z equals 10 plus. All more massive, brighter, more evolved than they should be. This isn't measurement error. It's not a few outliers. It's a pattern. And patterns demand explanations. So, what explains this? What could make galaxies form 10 times faster than models predict? What could make star formation 40 times more efficient? What could shut off star formation and age galaxies in a fraction of the normal time? The next act explores possible explanations. Some are conservative, tweaks to existing models. Some are radical, new physics, new cosmology, and some challenge everything we think we know about the universe. Let's start with the most conservative explanation, the one every scientist checks first. Are we sure these measurements are correct? Could the redshifts be wrong? Could these galaxies actually be closer than we think? Maybe at Z equals 5 or 6 instead of Z equals 10 plus ? That would make them much younger, giving more time for stars to form, solving the problem entirely. This is always the first hypothesis to test, because if the observations are wrong, there's no crisis. Models are fine, cosmology is safe, everyone goes home happy. So let's examine the evidence. Photometric redshifts are estimated from colors. You photograph a galaxy through multiple filters, different wavelengths, and measure how bright it is in each filter. The pattern of brightness tells you the redshift. This method works well, but has uncertainties. Typical error margins are delta Z, approximately 0.5 to 1. You might think a galaxy is at Z equals 11 when it's actually at Z equals 10 or Z equals 12. And sometimes photometric redshifts can be catastrophically wrong. A dusty galaxy at Z equals 2 can sometimes masquerade as a high redshift galaxy if its light is heavily absorbed by dust. This happened early in JWST's mission. Sears 93316 was initially reported at Z equals 16.7. Would have been the most distant galaxy ever found. Astronomers were excited. Papers were written. Press releases drafted. Then spectroscopic observations came in. The actual redshift? Z equals 4.9. Still distant. Still interesting. But not record-breaking. And not early enough to challenge models. The photometric redshift was wrong by a factor of 3. The galaxy was 10 billion years younger than initially thought. So yes, photometric redshifts can be wrong. But here's the thing. Many of the extreme JWST galaxies now have spectroscopic confirmation. Spectroscopy splits light into its component wavelengths. A spectrum. You see individual spectral lines from hydrogen, oxygen, other elements. These lines have known rest wavelengths. Measure how much they're shifted, and you get a precise redshift. Spectroscopic redshifts have uncertainties of delta Z, approximately 0.001. They're accurate to 3 decimal places. Maisie's galaxy. Z equals 11.44, spectroscopic. Jade's GSZ 13-0, Z equals 13.2, spectroscopic. Jade's GS as Z 14-0, Z equals 14.32. Spectroscopic. These aren't photometric estimates. These are confirmed distances. The galaxies are really at Z equals 11, 13, 14. They're really 13.4 to 13.5 billion light years away. The universe really was only 300 to 400 million years old. Could all the spectroscopy be wrong? Could there be systematic errors in JWST's spectrograph? Extremely unlikely. JWST's NIR spec instrument was extensively tested and calibrated. It's been used on thousands of targets. Redshifts match expectations for nearby galaxies where we have independent confirmation. And here's the clincher. Multiple independent teams using different analysis methods are getting consistent results. When several groups analyze the same galaxy and all get Z approximately 13, the measurements are probably right. So measurement errors can explain some anomalies. Sears 93316 turned out to be at Z equals 4.9, not Z equals 16.7. Fine. Crisis averted for that one. But the galaxies with spectroscopic confirmation? Those are real. Glass Z13, Maisie's galaxy, the Jade's galaxies. They exist at Z equals 10 plus, and dozens more candidates await spectroscopic follow-up. Will some be revised downward? Probably. But statistical analysis suggests most will be confirmed at Z greater than 10. The observations are real, which means the crisis is real. Okay, the galaxies are really at Z equals 10 plus. The distances are correct. The universe really was only 300 to 500 million years old. So maybe star formation just worked differently back then. Maybe the early universe had conditions that allowed stars to form much faster than today. Faster than our models account for. Maybe the problem isn't star formation. Maybe it's the scaffolding. The dark matter halos that galaxies form inside. Galaxies form where dark matter is most concentrated. Dark matter collapses first, forming halos. Then normal matter falls into those halos. Bigger halos attract more gas. More gas means more stars. So maybe dark matter halos formed earlier and larger than models predict. That would give galaxies more gas to work with, allowing them to form more stars. Here's a more exotic idea, one that's gained traction as JWST data has accumulated. Maybe supermassive black holes formed first, before galaxies, and these black holes seeded rapid galaxy formation. Here's how it would work. Normally, black holes form from stars. Massive stars collapse when they die, forming stellar mass black holes of approximately 10 to 100 solar masses. These black holes merge over time, gradually building up to supermassive black holes, millions to billions of solar masses, at galactic centers. This process takes billions of years. But what if supermassive black holes formed directly, without the need for stars first? In certain conditions, very dense gas, low metallicity, intense ultraviolet radiation from nearby sources, gas clouds could collapse directly into massive black holes. Instead of fragmenting into stars, the gas forms a supermassive star that immediately collapses into a black hole of 10,000 to 100,000 solar masses. This could happen as early as 100 to 200 million years after the Big Bang. Once you have a massive black hole, it accretes gas fast. Gas spirals into the black hole, releasing enormous energy. This energy heats and illuminates the surrounding galaxy. The black hole's gravity attracts more gas from the dark matter halo. The galaxy assembles rapidly around the black hole. In this scenario, the black hole comes first. The galaxy forms around it, rather than the black hole forming in an already existing galaxy. Potentially, black hole accretion can be very efficient. If a 100,000 solar mass black hole accretes at maximum rates for 200 million years, it could trigger the formation of billions of solar masses of stars. And there's some evidence for this. Several high redshift JWST galaxies show signatures of active galactic nuclei, AGN, supermassive black holes actively feeding. Finding AGN at Z equals 10 plus was itself surprising. Supermassive black holes shouldn't exist yet. But if DCBH is formed, they could explain both the black holes and the rapid galaxy formation. The problems with this idea: 1. DCBHs are theoretical. We've never directly observed one forming. 2. The conditions for DCBH formation are very specific and probably rare. You can't make every galaxy this way. 3. Even with DCBHs, you still need to form 10 to 100 billion solar masses of stars in 300 million years. The black hole helps, but it's not magic. 4. Red quiescent galaxies can't be explained by AGN. AGN heat gas and a trigger star formation. They don't shut it off and make galaxies red. So DCBHs might explain some of the JWST galaxies, the ones with AGN signatures, actively forming stars. But not all of them. Not the red dead ones. Not the ones with no AGN activity. It's part of the picture, but not the whole answer. We've explored tweaks, adjustments, exotic mechanisms within known physics. None of them fully explain the observations. Which brings us to the most radical possibility, the one astronomers hesitate to even mention because of how profound the implications would be. Maybe the problem isn't galaxy formation. Maybe it's cosmology itself. Maybe the universe didn't evolve the way we think it did. Maybe the expansion history is different. Maybe fundamental constants change over time. Maybe our entire framework is wrong. Let's explore very carefully what this would mean. Possibility 1. Modified gravity at early times. General relativity describes gravity. It's been tested extensively and works brilliantly in the modern universe. But maybe gravity worked differently in the very early universe. Maybe dark matter behaved differently. Maybe structure formation was accelerated by some modification to gravity that only operated at Z greater than 10. This is possible in principle. There are alternative theories of gravity. MOND, TEVES, others. But these theories were designed to explain galaxy rotation curves without dark matter. They weren't designed for the early universe. And modifying gravity has consequences. It changes the cosmic microwave background. It changes Big Bang nucleosynthesis, the formation of light elements in the first few minutes. It changes the expansion history. The CMB fits general relativity predictions with exquisite precision. Matching that precision with modified gravity is extremely difficult. So this path is treacherous. You're throwing away a century of confirmed predictions to fix one problem. Possibility 2. Varying physical constants. Maybe the fundamental constants of nature, the speed of light, the gravitational constant, the fine structure constant, were different in the early universe. If gravity was stronger, structures would form faster. If nuclear reaction rates were different, star formation might proceed differently. This sounds wild, but some theories predict varying constants. String theory, for instance, allows constants to vary as the universe evolves. The problem: we have constraints on how much constants can vary. From the CMB, from Big Bang nucleosynthesis, from quasar spectra at high redshift. Constants can't vary by much. Maybe a fraction of a percent, not the factors of 10 to 100 needed to explain JWST galaxies. So varying constants doesn't seem to help either. Possibility 3. Different expansion history. What if the universe expanded differently than we think? What if the time between z equals 10 and today was longer than 13.3 billion years? If the universe expanded more slowly in the past, there would be more time for galaxies to form. Problem solved. But this conflicts with everything else. The expansion history is constrained by Type Ia supernovae, standard candles showing accelerating expansion. The cosmic microwave background, which depends on expansion history. Baryon acoustic oscillations, standard rulers in galaxy distributions. Time delays in gravitationally lensed quasars. All of these independently confirm the current expansion history. Changing it would require all of these observations to be systematically wrong. That's unlikely. The fundamental issue with new physics explanations. Cosmology isn't one theory. It's an interconnected web of observations and predictions. The CMB constrains inflation, dark matter, expansion history. Big Bang nucleosynthesis constrains the baryon density and expansion rate at 3 minutes. Supernovae constrain dark energy and recent expansion. Galaxy clustering constrains dark matter and structure formation. Everything fits together. Change one piece and you break 10 others. To fix JWST galaxy observations with new physics, you'd have to rebuild cosmology from the ground up. And the new cosmology would have to match every other observation we've ever made. That's not impossible. Paradigm shifts happen. Cosmology has been revolutionized before. But it's the last resort. You exhaust every other possibility first. And we're not there yet, because there's still one more option. One we haven't fully explored. We've examined the explanations. Measurement errors explain some anomalies, but not all. Extreme star formation models can't reach the required rates. Dark matter halo formation would require changing inflation. Direct collapse black holes might help but aren't sufficient. And new physics would require rebuilding all of cosmology. None of the easy answers work. None of the hard answers are satisfying. So where does that leave us? In an uncomfortable place. A place of uncertainty. A place where the observations are solid, but the explanations aren't. This is what science looks like when confronted with the unexpected. Not clean, not resolved, just working through the possibilities. And the work is ongoing, right now. As you watch this video, astronomers are analyzing new JWST data, running simulations, proposing refinements to models. Maybe in a year, we'll have an answer. Maybe in 5, maybe in 10, or maybe these galaxies will force a genuine paradigm shift, a rethinking of how the universe evolved. We don't know yet, and that uncertainty, uncomfortable as it is actually what makes this exciting. Let's talk about what this means for science, for understanding, for the future. Let me tell you something important about science, something that doesn't always come through in headlines and press releases. This discomfort we're feeling, this uncertainty about whether JWST's galaxies are explainable within current models or require new physics, this is normal. This is how science works when it's actually working. New instruments always reveal surprises. Always. It's not a bug. It's a feature. When Galileo first pointed a telescope at Jupiter in 1610, he saw moons. 4 moons orbiting Jupiter. This was unexpected. The prevailing model said everything orbited Earth. Jupiter having moons challenged that model. It took time to work through the implications. Decades, actually. But eventually, those observations helped overthrow geocentrism. When Edwin Hubble measured galaxy velocities in 1929, he found something impossible. Distant galaxies were moving away from us. The farther away, the faster they receded. This contradicted the prevailing model of a static, eternal universe. Einstein himself had modified his equations to keep the universe static. He called it his biggest blunder. Hubble's observations forced a complete rethinking. The universe is expanding. It had a beginning. The Big Bang. Paradigm shift, caused by unexpected observations. When the Hubble Space Telescope conducted its first deep field observation in 1995, astronomers expected to see a few hundred galaxies. They saw 3,000. The universe was far more populated than models predicted. This didn't break cosmology, but it required refinements, updated models, better understanding of galaxy formation. Every major telescope has revealed anomalies, surprises, observations that didn't quite fit, and every time the scientific community goes through the same process. Step 1. Check for errors. Are the measurements right? Could instruments be malfunctioning? Are calibrations correct? Step 2. Explore explanations within existing models. Can we tweak parameters? Adjust assumptions? Account for the observations without changing fundamental physics? Step 3. If tweaks don't work, propose new mechanisms, new processes, new physics, new frameworks. Step 4. Test everything. Make predictions. Design new observations. Run simulations. See which explanations hold up. Step 5. Refine or revolutionize. Either models get updated with new insights, or, rarely, the entire paradigm shifts. We're currently between steps 2 and 3 with JWST's massive galaxies. Some proposed explanations are refinements, enhanced star formation, direct collapse black holes. Others are more radical, modified gravity, different expansion history. The work is ongoing. Papers are being published weekly. Simulations are running. New JWST observations are being analyzed. This process takes years, sometimes decades. The discovery of accelerating expansion was made in 1998. We're still refining dark energy models 27 years later. We still don't know what dark energy is, but the process is working. Observations constrain theories. Theories make predictions. New observations test predictions. Knowledge advances. Uncertainty is uncomfortable, but it's also honest. It means science is confronting something genuinely new, not just confirming what we already believed. And that's exciting. Here's what's remarkable. Even if half of JWST's extreme galaxy candidates turn out to be measurement errors or misinterpretations, we're still learning something profound. Because even the confirmed galaxies, the ones with spectroscopic redshifts, solid mass estimates, and multiple independent confirmations, are more massive and more numerous than models predicted. Maybe not 100 times more massive. Maybe only 3 to 10 times more massive. But that's still significant. That's still a challenge to models, and it's already teaching us things. Lesson 1. The early universe was more active than we thought. Star formation started earlier, proceeded faster, and produced more massive galaxies sooner than models predicted. This might not require new physics. It might just require updating star formation, efficiency parameters, adjusting feedback models, or accounting for processes we underestimated. But it's a genuine insight. The universe didn't wait around. It got busy, fast. Lesson 2. Galaxy formation is more diverse than we expected. We expected early galaxies to be uniformly small, irregular, blue, and actively star-forming. Instead, we're finding diversity. Some are actively forming stars. Some are quiescent. Some are blue. Some are red. Some are compact. Some are extended. This diversity emerged early. Within the first few 100 million years, galaxies were already exploring different evolutionary paths. That's unexpected, and it tells us that galaxy evolution isn't one size fits all. Even at the earliest times, there were multiple ways to build a galaxy. Lesson 3. Supermassive black holes formed earlier than we thought. Several high redshift JWST galaxies show signs of active galactic nuclei. Black holes millions of solar masses existed when the universe was 300 to 400 million years old. This was surprising. We thought supermassive black holes took a billion years to form, but they're there, at Z equals 10 plus, already massive, already feeding. This suggests black hole formation mechanisms we didn't fully appreciate. Maybe direct collapse, maybe super Eddington accretion, maybe something else. But it's real data, real discoveries, expanding our understanding. Lesson 4. Models need refinement. This isn't a failure. Models are meant to be tested and refined. The standard galaxy formation model, built over decades, was based on Hubble observations going back to Z approximately 6 to 8. It extrapolated to earlier times. JWST is now testing those extrapolations and finding they don't quite work, so models will be updated, star formation prescriptions adjusted, feedback mechanisms reconsidered, timescales revised. This is how science progresses. Observations push models. Models improve. Understanding deepens. Even if cosmology doesn't need a revolution, if this is just a refinement, we're learning that the early universe was different from what we expected. More vigorous, more efficient, more diverse, more surprising, and that's valuable knowledge. The story isn't over. JWST's mission has barely begun. Launched in December 2021, operational since July 2022. Its mission is planned for 10 plus years, possibly 20 years if fuel and instruments hold up, which means we're seeing the first 10% of JWST's discoveries. The first deep fields, the first high redshift galaxies, the initial surprises. There's so much more coming. JWST's ongoing and future programs. Deeper fields. JWST will observe patches of sky for even longer exposures, finding fainter, more distant galaxies. We might push past Z equals 15, maybe Z equals 20. See galaxies when the universe was 100 to 200 million years old. Spectroscopic surveys. Follow-up spectroscopy of all the photometric candidates. Confirming redshifts, measuring metallicities, determining stellar populations. This will turn uncertain candidates into solid data. Detailed studies, high resolution, imaging resolving galaxy structures, mapping star formation within galaxies, measuring gas kinematics, understanding how these galaxies work internally. Time domain observations, repeated observations of the same fields, looking for variable sources, supernova, AGN variability, transient events. These reveal physics we can't see in single snapshots, and JWST isn't alone. Other telescopes are joining the hunt. Extremely Large Telescope, ELT, 39-meter ground-based telescope, first light expected 2028, will provide spectroscopy complementing JWST's imaging. 30-meter telescope, TMT, 30-meter telescope planned for late 2020s, similar capabilities to ELT, Nancy Grace Roman Space Telescope, NASA's next flagship space telescope, launching 2027. Designed for wide-field surveys, it will find thousands of high redshift galaxies for JWST to study in detail. Square Kilometre Array, SKA, radio telescope array detecting 21 centimeter radiation from neutral hydrogen in the early universe. Will map the cosmic dark ages and reionization. The next decade will be transformative for early universe studies. By 2030, we'll have hundreds of spectroscopically confirmed Z greater than 10 galaxies. detailed studies of their properties, statistical samples large enough to test models rigorously, independent observations from multiple instruments. The current uncertainty, are these galaxies explainable or paradigm-breaking, will be resolved. We'll either understand them within refined models, or we'll be forced to accept that cosmology needs updating. Either way, we'll know. And that's the beauty of science. Uncertainty doesn't last forever. Observations accumulate, evidence mounts, answers emerge. Maybe the answers are surprising, maybe they're mundane, but we get answers. The universe doesn't keep secrets permanently. It yields them to patient observation and careful analysis. We're living through the discovery phase, the exciting, uncertain, frontier period. Enjoy it, because in 10 years, this will all be textbook material. Today's impossible galaxies will be understood, categorized, and explained in undergraduate astronomy courses. But right now, they're mysteries, and we get to watch the mystery unfold. Let's step back, way back, and think about what this all means. We built a telescope. Humanity pooled resources, knowledge, and effort. We designed instruments to detect infrared light. We launched a tennis court-sized spacecraft to a point 1.5 million kilometers from Earth. We cooled it to 40 Kelvin. We unfolded mirrors with nanometer precision. And then we pointed it at empty patches of sky. And we looked. What did we find? Galaxies. Thousands of them. Billions of light years away. Shining with the light of billions of suns. Existing when the universe was young. And some of those galaxies surprised us. They were bigger than expected, brighter than predicted, more mature than models allowed. They challenged our understanding, made us question our models, forced us to consider that maybe, just maybe, we don't understand the early universe as well as we thought. That's not a failure. That's a success. Because the goal of science isn't to confirm what we already believe. It's to discover, to learn, to push into the unknown and see what's there. And when what's there doesn't match expectations, that's when science gets interesting. JWST's massive galaxies might not break cosmology, they might just bend it, require refinements, updates, better models, or they might genuinely revolutionize our understanding. Force a paradigm shift, reveal that the early universe operated under different rules than we realized. We don't know yet, and that's okay. Because here's the philosophical point that matters. The universe doesn't care about our models. It doesn't care about our theories, our expectations, our assumptions. The universe just exists, governed by physical laws, evolving according to those laws, completely indifferent to whether humans understand it or not. For 13.8 billion years, galaxies formed, stars ignited, black holes grew, structures evolved, without any humans watching, without any consciousness observing. The universe did its thing, and now, in the last microsecond of cosmic history, one species on one planet has developed the technology to look back, to see cosmic history, to measure, analyze, and understand. That's extraordinary. We're not just observers. We're the universe observing itself. Matter organized into patterns complex enough to comprehend the cosmos that created it. Carl Sagan said, "We are a way for the universe to know itself." JWST is an extension of that, a technological eye allowing the universe to see its own infancy. And what it's seeing doesn't match expectations. The infant universe looks different than we thought. Maybe the universe had a growth spurt we didn't account for. Maybe it matured faster than our models predicted. Maybe conditions in the cosmic nursery were stranger than we realized. We'll figure it out. with more observations, better models, refined theories, but the fundamental wonder remains. We looked across billions of light years, across billions of years of time, and we saw. We saw galaxies forming when the universe was 2% of its current age. We measured their masses, their brightnesses, their distances. We confronted the impossible and asked, how? That question, that honest, humble confrontation with the unexpected, is what drives science forward. JWST found galaxies that challenge cosmology, and cosmologists responded with, tell us more. Not denial, not dismissal, but curiosity, excitement, the thrill of discovery. Because even if these galaxies remain unexplained for years, even if they force us to rewrite textbooks, even if they reveal that our understanding of the universe is incomplete, that's not a problem. That's a gift. The universe is stranger than we thought, and we get to figure out why. If you've made it this far, thank you. We've traveled from the familiar, galaxies, stars, cosmology, into the unknown, into a realm where observations don't match theory, where the universe is revealing surprises, where answers are uncertain. We've examined JWST's impossible galaxies, massive structures at Z equals 10, 11, 12, 13, existing just 300 to 500 million years after the Big Bang, containing billions of stars, some already aged and red. We've explored why they're impossible according to standard models, why there wasn't enough time for that many stars to form, why stellar masses exceed predictions by factors of 10 to 100. We've investigated explanations. Measurement errors explain some, but not all. Extreme star formation can't reach the required rates. Dark matter modifications require changing inflation. New physics would require rebuilding cosmology, and we've confronted the uncomfortable truth. We don't have a complete answer yet. Maybe in a year, maybe in 5, but not today. Subscribe if you want updates as this story unfolds, as new JWST data arrives, as models are refined, as the mystery resolves or deepens. Comment below with your thoughts. Which explanation do you find most plausible? Are these galaxies genuinely paradigm-breaking, or will they be explained within existing physics? What do you think is going on? Share this video with anyone interested in cosmology, astronomy, or the process of science confronting the unexpected. This is frontier science happening in real time. One final thought. James Webb Space Telescope cost $10 billion to build. It required decades of planning, engineering, and construction. Thousands of people contributed to making it possible. And what did it find? Immediately, within months of operation? Evidence that the universe is stranger than our theories predicted. Some might see that as a failure. $10 billion to discover we were wrong, but that's exactly backwards. JWST succeeded perfectly. It did exactly what great telescopes are supposed to do. Show us something we didn't expect. Challenge our assumptions. Reveal that the universe is more complex, more surprising, more mysterious than we imagined. We didn't spend $10 billion to confirm what we already knew. We spent it to discover. And we're discovering that the early universe was more active, more efficient, more vigorous than models predicted. Maybe that requires small adjustments. Maybe it requires big changes. Maybe, just maybe, it requires a revolution. But whatever the answer, we're learning. We're advancing. We're getting closer to understanding how the cosmos actually works. These galaxies shouldn't exist, but they do exist. The data is clear. The observations are solid, which means our job now is to figure out why, to understand what we're missing, to refine our models, or revolutionize our theories. That's not a crisis, that's science. James Webb found galaxies that break cosmology. And that's the most exciting thing it could have done, because now we get to fix it.